Welcome everybody. This recitation will be on duality and support vector machines. By reviewing the chain function and its relation to duality. Then we will go through some examples of deriving the dual function in the dual problem. Then we will discuss support vector machines as an interesting and famous example of duality being useful. So we will go through primal and dual formulations of the hard margin support vector machine. Then we will see the soft margin version and its relation to the hinge loss. So let's get started. The Lagrangian. We have a minimization problem where we want to minimize f of x with respect to x, subject to some equality constraints of the form gi of x is equal to 0. We have seen in class that the way to solve such problem is to add a Lagrange multiplier for each constraint. And that gives us the Lagrangian function, which is a function of the primal variables, the variables in our optimization problem, and the Lagrange multipliers. We have seen that to solve the problem, we can set the gradient of the Lagrangian to 0. So if we set the gradient of the Lagrangian with respect to ui to 0, we get that gi of x is equal to 0. If we set the gradient with respect to x to 0, we get that the gradient of f of x plus sigma I ui, the gradient of gi of x, is equal to 0. The first condition means that the solution has to be a feasible point. It satisfies all constraints. The second condition tells you that the gradient of the objective function at the solution is a linear combination of the gradients of all of the constraints. And that means you cannot move from the solution and decrease the objective function except by violating at least one constraint. Because to move without changing the value of gi of x, you need to move in a direction that's orthogonal to all constraints, to the gradients of all constraints. And this condition tells you that such a direction will not change your objective function. So now let's consider the case where we have an additional set of inequality constraints in the form of hj of x less than or equal to 0. And we apply the same principle by adding a Lagrange multiplier for each constraint to get a Lagrangian function. Now we'll see how this Lagrangian function relates to duality. So we have the primal problem, which is the original problem we want to solve. It's a minimization problem with respect to subject to some equality and inequality constraints. And I claim that this is equivalent to solving this minimax problem on the Lagrangian. So that means for each x, I choose lambda and u that maximize this Lagrangian for this particular x. And then I choose x that minimizes this maximization. To see why these two problems are equivalent, consider the case where x violates an equality constraint. That means for some I, gi of x is not equal to 0. Then you can choose ui to be arbitrarily large, positive or negative depending on the sign of gi of x, and make the Lagrangian grow up indefinitely. And that means the solution to this maximization will be infinity. Similarly, if x violates an inequality constraint, that is hj of x is greater than 0 for some j, then we can choose lambda j to be arbitrarily large to make the whole Lagrangian become arbitrarily large. And again, that means the solution to the maximization will be infinity. If x is feasible, on the other hand, gi of x will be equal to 0 for all i's, and that means this summation will vanish. Also, hj of x will be either 0, in case of which this term will vanish, or hj of x will be strictly less than 0, in case of which lambda j has to be 0 to maximize the Lagrangian, because we constrain lambda to be greater than or equal to 0. And so in all cases, if x is feasible, this summation will also vanish. And this tells you why it is important to choose the sign of lambda j carefully. If we have a less than or equal constraint, this sign has to be positive. On the other hand, if we have constraints that are greater than or equal, this sign has to be negative. Because again, we want, for any feasible x, we want this maximization to be obtained at lambda j equal to 0. So, for a feasible x, we are just left with f of x. So, this entire maximization expression can be replaced with this two-way definition. So we are minimizing a function that's equal to f of x if x is feasible and infinity otherwise. And you can easily see that this is equivalent to minimizing f of x such that x is feasible. So now we have seen that the primal problem is a minimax problem on the Lagrangian. The dual problem is obtained by first obtaining the dual function. The dual problem is obtained by simply swapping the order of maximization and minimization. So now we have a problem where we want, for each choice of lambda and u, we find x that minimizes the Lagrangian for this choice of lambda and u, and then we pick lambda and u that maximize this minimization. Now, this minimization expression is a function of lambda and u, which the Lagrange multipliers, or we call them the dual variables. This function is called the Lagrangian dual function. The dual function is concave regardless of the convexity of the primal. Why? Because if you fix x at a particular value, then this Lagrangian is just a linear function of u and lambda. And so for the Lagrangian, the dual function is just a pointwise minimization of functions that are linear in u and lambda. And this is known to be concave. Also, the dual function is a lower bound on the primal or objective function. To see that, let's consider this illustration. So, we have the Lagrangian function, which is a function of the primal variable and the dual variable. We are considering only inequality constraints for simplicity. And for visualization purposes, I assume that the variables are discrete. So we have discrete choices of x and discrete choices of lambda, and for each x and lambda, we have a value of the Lagrangian. In reality, you can assume that we have a grade of infinite resolution. So, the way the primal problem works is that for each choice of x, that is for each row, we choose lambda that maximizes the Lagrangian for that x. And then we choose the x that minimizes the Lagrangian from these choices. The dual problem works the way around. So for each lambda, we choose the x that minimizes the Lagrangian, and from this minimization, we choose the lambda that corresponds to the maximum one. And now we claim that the primal is an upper bound on the dual. To see why this holds, suppose that x star is the solution to the primal. And that means the minimum value of the primal objective is the Lagrangian at x star and lambda star. Then, by definition of the primal, the Lagrangian in this cell has to be greater than or equal the Lagrangian at any other choice of lambda for the same x star. But according to our definition of the dual, for any lambda, the value of the dual has to be less than or equal the value of the Lagrangian at any other x for the same lambda. And so this gives us the inequality that the primal solution, which is the minimum of the primal problem, is an upper bound on the dual. The difference between the primal minimum and the dual maximum is called the duality gap. When duality gap is equal to 0, we call this situation strong duality. And that means the dual function becomes a tight lower bound on the primal objective function. And so our natural question would be, when does strong duality hold? In other words, when does this point become also a solution to the dual? And the claim is, strong duality holds when this point is a saddle point. That means the Lagrangian at this point is greater than the Lagrangian at any other choice of lambda for the same x, but less than the Lagrangian at any other choice of x for the same lambda. And this is called a saddle point, because if you take a cross section of the Lagrangian at this direction, you will see x star and lambda star as a maximum point. But if you take a cross section in this direction, you will see x star and lambda star as a minimum point. And so it's maximum in some direction and minimum in the other one. And so it's like the center point of the saddle of a horse, and hence it's called the saddle point. So this is a necessary and sufficient condition for strong duality, that the optimal point for the solution to the primal is a saddle point in the Lagrangian function. And to see why this is a necessary and sufficient condition, well, it's necessary by the definition of the dual, because this point is a solution to the primal. It has to be less than the Lagrangian at this point has to be less than the Lagrangian at any other choice of x, because that makes this point a solution to the dual. And because it's a solution to the primal, then it has to be, the Lagrangian at this point has to be greater than the Lagrangian at any other choice of lambda for the same x. And to see why it is sufficient, we have already established an inequality that the solution to the primal is an upper bound on the dual. Now you are given an extra piece of information that this upper bound is actually the dual function evaluated at lambda star. And so you have the dual function at lambda star is equal to a value that we know to be an upper bound on the dual. And so it has to be the dual solution. And so we have seen that if the primal solution is a saddle point in the Lagrangian, this is a necessary and sufficient condition for strong duality. If strong duality holds, KKT conditions apply to the optimal point. The first three conditions are kind of natural. So the point has to be stationary point in the sense that the gradient of the Lagrangian has to be 0, the gradient with respect to both primal and dual variables. The solution has to be feasible, of course, satisfying all equality and inequality constraints. And it has to be feasible in the dual sense as well. So inequality constraints, remember we constrain the Lagrange multipliers to be greater than or equal to 0. This has to apply to the optimal point. Another constraint is complementary slackness. This complementary slackness applies to inequality constraints and basically tells you that if lambda I is not equal to 0, then hi of x is equal to 0. That means if the Lagrange multiplier is not 0, then the corresponding inequality constraint is barely satisfied. It's just on the boundary. On the other hand, if the inequality constraint is strictly satisfied, the I has to be equal to 0. This complementary slackness constraint will see that it will be very useful when we consider support vector machines. One important thing to note is that KKT conditions are always sufficient, but they are necessary under strong duality. In many situations, we design optimization algorithms that search for points that satisfy KKT conditions. So we use KKT conditions as a characterization for optimality. In these cases, we want KKT to be both sufficient and necessary. Because if KKT is not sufficient, then the algorithm might return a suboptimal point. Because satisfying KKT condition does not necessarily imply, if KKT is not sufficient, satisfying KKT does not imply the point is optimal. And we want KKT to be necessary, because if this is not the case, the algorithm might return no solution, even though an optimal point might actually exist, but it just doesn't satisfy KKT conditions. So that's why when we use KKT conditions as a characterization for the optimal point, we want them to be both sufficient and necessary. And that means we want to verify strong duality, but verifying the saddle point criterion might be difficult. Fortunately, there are other sufficient conditions for strong duality that are easier to check. For example, if you find the feasible point that strictly satisfies all inequality constraints, then strong duality holds. This is a stronger version of what's called Slater's condition. So, let's apply these concepts on some examples, and we will start with linear programs. We already seen in class how to find the dual LP for a given LP, and we have seen how this dual LP lower bounds the solution of the primal LP. What we are going to see here is that by applying the general definition of the dual function, you get the dual LP. Even though the general definition of the dual function does not seem to explicitly include constraints, we will see that applying this definition in the context of LP gives rise to a dual problem that contains constraints, which is what you have seen in class. So the primary problem for LP is minimizing a linear function in X, C transpose X, subject to a set of constraints that can be written in matrix form. AX is greater than or equal to B, where this greater than or equal means pointwise greater than or equal. That means each coordinate of this vector has to be greater than or equal the corresponding coordinate of this vector. So, let's formulate the Lagrangian. So, we add a Lagrange multiplier for each constraint. That gives us a vector of Lagrange multipliers. And notice here that since we have greater than or equal constraints, then we add our Lagrange multipliers with minus sign. Let's take the dual. So we compute the dual by minimizing the Lagrangian. We compute the dual at a particular lambda by minimizing the Lagrangian with respect to x for that lambda. If we take the gradient with respect to x and set it to 0, then we simply get C minus A transpose lambda is equal to 0. And we can note that we can write the Lagrangian in the form C minus A transpose lambda transpose x plus lambda transpose B is equal to 0. And now we know that this is equal to 0, and so we are left with lambda transpose B. And so we can say that the dual problem is just maximize lambda transpose B. However, this is not true. We need to keep this condition as a constraint. Even though we substituted this condition in the Lagrangian to come up with this lambda transpose B, that's not sufficient. We need to keep it as a constraint. And why is that? Basically, a typical situation would be you set the gradient with respect to x to 0, and you end up with something like x is equal to something that's function of lambda. Let's call it like g of lambda. And so what you do is that you then go to the Lagrangian and replace each occurrence of x with g of lambda, and this becomes your dual. This is the typical case. And in this case, you usually don't need to introduce additional constraints because this condition does not enforce your choice of lambda. For any lambda you pick, you have a corresponding x. On the other hand, this condition does not involve x. It just constrains your choice of lambda. It says for the Lagrangian to have a stationary point so that you can actually do minimization, your choice of lambda has to satisfy this condition. Otherwise, you are minimizing this function with respect to x. And if this is not 0, then, since x is unconstrained, then you can get the function to be as small as you want. And so this minimization would be minus infinity. And hence the dual function is not, it's not accurate to say that the dual function is lambda transpose b. Rather, it's lambda transpose b only if C A transpose lambda is equal to 0. Otherwise, the dual function is actually minus infinity. And so this is the function that we want to maximize in the dual problem. And it's equivalent to say that the dual problem is to maximize lambda transpose b subject to these constraints. And so this is how it happens that applying the definition of the dual function and the dual problem can give rise to additional constraints on the dual. Let's consider another example. In this example, we will use duality to transform lasso into a quadratic program. So, if you recall lasso, the primary problem is the minimization of square error of training data with respect to the weights W, in addition to an L1 penalty on the weights. What's the dual function in this case? Well, the dual function is the function of the Lagrange multipliers. But here we don't have constraints, and hence we don't have Lagrange multipliers. And so the dual function is actually a constant that tightly lower bounds the primal. The dual function is just the solution of the primal and its constant. And this doesn't seem to help that much. And so we will we will reformulate the problem in a way that involves constraints but results in an equivalent problem. So we will replace xw by a variable z and add a constraint that z is equal to xw. Now we can take the dual, which is equal to the Lagrangian being minimized with respect to z and w. So let's do the minimization. If we set the gradient with respect to z to 0, we get y minus z plus 0 plus lambda equal to 0, which gives z is equal to y minus lambda. Now, handling w is a bit more tricky, so let's consider just a single wi. In this case, we have lambda times the derivative between quotes of the absolute value of lambda I minus the ith coordinate of x transpose lambda has to be equal to 0. And that means x transpose lambda, this is a vector, the ith coordinate of this vector divided by lambda has to be equal to, again, derivative between codes. We know that the absolute function is not differentiable at 0. We know that the derivative is +1 for positive w, -1 for negative w, but the function is not differentiable at 0. And so we resort to subdifferentials, which were introduced in our previous recitation. Basically, the function is differentiable, the subdifferential is just the derivative. So the subdifferential at a positive w will be +1, and it will be -1 for a negative w. But the subdifferential at a point like 0 is basically the set of all slopes of lines that intersect with this point but still remain below the function. And so any line with a slope that's between -1 and +1 satisfies this condition. And so the subdifferential at 0 is the interval -1 and 1. And so now we know that this subdifferential cannot go beyond the interval -1 and 1 for any w. And this expression, this equation is not really accurate. It should be, this equality should be, belongs to, because the subdifferential is a set of values, not just a single value. But in order to have a valid solution, the left hand side has to be between -1 and 1. Otherwise, there is no wi that can include the left hand side, for which the subdifferential can include the left hand side. And so that means x transpose lambda I divided by gamma has to be between -1 and 1. And you can easily write that as x transpose lambda I as an absolute value is less than or equal lambda. And since this applies for each I, then we can write that compactly in this form, because recall that the infinite norm of a vector is the maximum absolute value of its coordinates. And so now we have this dual problem. Is this a quadratic problem? And the answer is yes, because this can be written as minimize a quadratic function of lambda subject to linear constraints. So this becomes 0 and x transpose lambda I is greater than or equal lambda, and x transpose lambda minus x transpose lambda I is less than or equal lambda. All these are linear constraints, so we get a quadratic objective function with linear constraints, which is a quadratic program. Of course, this was a sort of an exercise of how you can transform an optimization problem to a quadratic program, even though that was not obvious at the first glance. This transformation may not have significant practical value, because there are efficient algorithms for solving the Lasso problem that are more efficient than using a general purpose QP solver, but this example was for the sake of an exercise. Now let's discuss a real example where duality is useful in the sense that it can expand the capability of your algorithm and give you useful insights on the problem. So, support vector machines. And as you have seen in the lecture, an SVM is based on finding the optimal separating hyperplane. And the optimality criterion here is the margin. So essentially we want to find the hyperplane that keeps training points as far away as possible from the decision boundary. And not only is the dual formulation useful for this problem, even the way the primal problem is formulated is a nice example of how you can formulate a problem in a nice way that's solvable. Whereas if you formulate the same description naively, you can end up with a terrible problem that's very difficult to solve. And so it's a nice exercise to first come up with the primal formulation of the support vector machines. So suppose we know nothing about SVM, and just someone tells you, I want to find a hyperplane that maximizes the distance between the training points and the decision boundary. Well, the distance from a point xi to the hyperplane w transpose x plus b is 0. So this is a hyperplane. The distance between this point and the hyperplane is given by w transpose xi plus b divided by the norm of w. This is the distance. So this could be a free parameter x, and this is the distance between xi and that hyperplane. Then the margin is just minimize yi di. What does that mean? Notice that I wrote distance between quotes because this is a signed quantity. It depends on which side of the hyperplane you are in. And basically this quantity is positive if you are on the right side of the hyperplane and negative if you are on the wrong side of the hyperplane. And since being right or wrong depends on your class, that's why we multiply by yi, which is either positive 1 or negative 1 depending on the class. And so if we just do simple substitution, we get this form for the margin. And now to maximize the margin, we basically maximize this objective function with respect to w and b. And this looks quite rather unpleasant. So you have a maximization of 1 over the norm of your primal variables and then multiply it by a minimization of something. This is rather unpleasant. But there's a more fundamental flaw. This problem has no unique solution, because for any w and b that solves this problem, you can scale w and b by an arbitrary positive quantity, and that will keep the decision boundary and the margin unchanged. And so we need to constrain the problem to find a unique solution. And at first glance, this might seem to be making the problem even more unpleasant. But if you choose your constraints wisely, you can actually simplify the problem. And an actual first guess would be to choose the norm of W, to restrict the norm of W to be 1, so that you get rid of this division. But you still face this minimization, which is not convenient. A better constraint would be, well, since this is an annoying term, let's constrain it to be 1, and so we don't need to worry about it in the objective function. Now we are left with this 1 over norm W, but this can be easily written as minimize the norm of W squared. But we still have a constraint of the form minimize I, this linear term, is equal to 1. But we can write that as this constraint is this linear term is greater than or equal 1 for all I. And this gives us an equivalent problem. Is it equivalent? Well, strictly speaking, the answer is no. Because if this term is greater than or equal to for all I, then this is still a feasible point in this representation, in this problem. But it's not a feasible point here. However, if you happen to get a solution where for each training point this function is greater than or equal to, then that means your weights, the magnitude of your weights is larger than necessary. And this will be penalized by the objective function. So the objective function will force the weights to be as small as possible to satisfy this constraint. And so you will end up having the minimum value of this term equal to 1. And so the two problems are equivalent in the sense that they will end up giving the same solution. But they differ in their feasibility region. They differ in the set of weights that are feasible. So we end up with this is called the canonical representation of support vector machines of the maximum margin problem. And now you can see that we started with an unpleasant formulation, but by cleverly choosing the constraints, we ended up with a quadratic problem. And now we can use a QP solver to solve this quadratic problem. So what's the buzz about this thing in support vector machines? Well, let's see. Let's just take the dual. So first we take the Lagrangian. So we will add a Lagrange multiplier for each constraint. And remember, this is a greater than or equal constraint, and so we add the Lagrange multipliers with a negative sign. Then let's take the gradients with let's set the gradient of the Lagrangian with respect to the primal variables to 0. So if we set the gradient with respect to W to 0, we get this condition. And now this condition basically tells you that W is a weighted combination of the training examples. And this is a kind of a condition where you can just plug this into the Lagrangian and you are done, because it doesn't constrain your choice of the alpha i's. On the other hand, if we optimize the Lagrangian with respect to B, we get this condition. This condition constrains your choice of alpha I to satisfy this equality. And so we can plug these two conditions into the Lagrangian. However, this condition has to remain as a constraint because it restricts your choice of alpha I. If your alpha violate this constraint, then the value of the dual function will be minus infinity. And if we do the substitution, we will get this dual problem. Maximize minus half arithmetic function of the alphas plus alpha I subject to some linear constraints in the alpha. So this is the constraint that we kept, and this is the constraint we always have on for inequality Lagrange multipliers. So this is just another QP. So what benefits did we get from that? The first benefit is that now training examples are only used in terms of as inner products, and that means we can apply the kernel trick. By applying the kernel trick, we can replace this inner product with an arbitrary kernel function if the kernel function is positive definite. Then applying the kernel function implicitly transforms our training data to a high dimensional feature space, and this feature space can be even infinite dimension, which means there is no way to explicitly represent the weights and solve the primal problem. Also, remember, complementary slackness condition for KKT means that alpha I times f of xi yi is equal to 0, where f of xi is the application of the weights, basically W transpose xi plus b. This is equal to 0, which means if this term is greater than 0, that is, if your point is away from the decision bound, from the margin, then the Lagrange multiplier has to be 0. In the other way around, if for some training point the Lagrange multiplier is not 0, this point has to be exactly on the margin. What does that mean? That means our weight vector is a combination of the training points, but points that are far from the margin receive 0 weights, and that means you care only about points that matter in deciding the decision boundary. Points that are deep in the distribution that are deep in the region of each class are not important, and so they are discarded. And this is why support vector machines are categorized as what's called sparse kernel machines, in the sense that you don't need, when you do prediction, you don't need all training data, as opposed to many other kernel-based methods. You need only training data that matters in determining the decision boundary, which are points that are on the margin. Also, there are a number of efficient optimization algorithms for support vector machines that are designed based on the principle of satisfying KKT conditions. And these are more efficient than using a general QP solver. Now, once we have trained the SVM, we want to use it to classify at this point. Well, we compute the scoring function. We basically apply the weights, but remember we don't have an explicit form of the weights. We just have the weights as a sum of training points, and so the inner product between the weight vector and the training point is just the sum, the weighted sum of inner products between the new point x and the support vectors. And so this inner product can be replaced by the kernel function. And we add the bias term. We haven't talked about how to compute the bias term, but it can be easily computed using the fact that for any support vector, yi f of xi is equal to 1, because it's exactly on the margin. So you can use any support vector and compute b. However, for numerical stability, what's typically done is that you average over all support vectors. Now, let's see the soft margin version of SVM. And first, let's look at the hard margin SVM from another perspective. So, we formulated the hard margin SVM as a constraint optimization problem. But we can also formulate it this way. We are minimizing the half square norm of W subject to some constraints, and we can represent these constraints as a function that's equal to 0 if the constraint is satisfied and equal to infinity otherwise. And so this function can be plotted this way. And if we look at this rotation, it's very similar to what we have seen in, for example, linear regression, where you have a loss function, for example, squared loss for linear regression, and a regularization term. We have the same situation here, except that the loss function is a kind of a very harsh loss function that's equal to infinity not just if you are misclassified, if you get even into the margin, the loss function becomes infinity. And so you can easily see that if the problem is not linearly separable in the feature space, then there is no solution for the hard margin SVM. And so we would like to relax this loss function a little bit. So we will replace this harsh term. We will replace it with a function that's equal to Cx rather than infinity when x is greater than or equal to 0. That is, rather than penalizing the violation of the constraint with an infinite penalty, we penalize it with some finite penalty that increases with the amount of violation. And so when we plot this loss function, it basically looks like this. Basically, we decrease the slope from infinity to C. And this loss function is called the hinge loss function. And we can basically reformulate the problem as C times the amount of violation plus the regularization term, where this plus subscript, this subscript means that this expression equates to 0 if whatever inside is negative. So if you are in the right side and you are far from the margin, then there is no penalty. Once you get into the margin, there's some penalty that increases the more you get into the margin. So this is a loss function view of soft margin support vector machine, but it's also equivalent. There's also an equivalent formulation in terms of margin constraints. And this formulation is that rather than minimizing the square norm of W, we minimize the square norm of W plus the summation of slack variables, which indicate the amount of violation. And so if we have the decision boundary, we have the margin, some points will satisfy the margin constraint, others will not satisfy. So for example, we might have a point that gets into the margin, and it can get into the margin a bit, it can get very deep into the margin that it actually goes to the wrong side. And so this relaxation allows for non-linearly separable cases. However, this violation is penalized, and the penalty increases as the violation increases. And so now, rather than requiring each point to be of distance, or to have a scoring function of 1, exactly to have a scoring function greater than or equal to 1, we now say that it has to be greater than or equal 1 minus I. And we have to constrain zeta I to be greater than or equal to 0. Why is that? If zeta I is equal to 0, then the point is either on the margin or on the right side and far from the margin. If zeta I is greater than 0 but less than 1, then the point can be within the margin but still on the right side of the classification boundary. If zeta I is larger than 1, then the point is allowed to even get to the wrong side of the classification boundary. Now, if zeta I is less than or equal to 0, then basically some point that's deep into the region of the class of stars will have the corresponding zeta I be negative. And that means points that are well behind the margin will have the negative zeta I's, and these negative zeta I's will decrease this penalty because you compute the penalty by summing over all training points. And we don't want that. We don't want points that are well beyond the margin to affect the penalty on points that really matter when determining the decision boundary. Otherwise, you can have a point that that's very far from the boundary, and you are basically ready, you are happy with having a point that's very far from the boundary and having many points basically on the wrong side of the decision boundary, just because the penalties caused by these points is compensated by a point that's very far from the decision boundary and is on the right side. So this is the equivalent formulation of the soft margin SVM, and again you can show that these two formulations are equivalent in the sense that they give the same solution. So, to conclude this station, we have seen that duality allows for establishing a lower bound on a minimization problem. The key idea is that minimax upper bounds max-min. So min-max is the min-max of the Lagrangian is the primal, max-min is the dual. And we have seen that strong duality implies the necessity of KKT conditions, and KKT conditions are always sufficient for optimality. We have seen duality on SVMs, and we've seen that the dual formulation allows for applying the kernel trick, and that due to complementary slackness, the model actually uses a small set of support vectors rather than using the entire training data to classify new points. We have also seen soft margin SVM, and we have seen that it's equivalent to minimizing hinge loss with a regularization term on the square loss of W. Here are links to additional resources that